There exist many different filters, and filters are used in many different applications. Usually, one of the 4 following standard filters is used. Filter classifications or specifications usually refer to properties of the frequency response as a function of omega. For instance, the frequency response of an ideal low-pass filter is specified to be equal to 1 up until the cutoff frequency, and then dropping down to 0 and staying equal to 0 for all frequencies above the cutoff frequency omega c. In contrast, the frequency response of an ideal high-pass filter is specified to be 0 for all frequencies up until the cutoff frequency omega c, and then 1 for all frequencies above the cutoff frequency. The frequency response of an ideal band-pass filter has 2 cutoff frequencies, omega c1 and omega c2. The frequency response for all frequencies in between those 2 cutoff frequencies is defined to be 1, and for all other frequencies the frequency response is equal to 0. Similarly, the band stop or notch filter also has 2 cutoff frequencies, omega c1 and omega c2, but the frequency response is equal to 1 for all frequencies below omega c1 and above omega c2, and 0 for all frequencies in between the 2 cutoff frequencies. These 4 filter classifications are used to specify ideal filters. They all have in common that they have sharp transitions, they don't have a phase angle, which implies that there would be no delay between the input and the output signal, and h of omega is equal to 0 for a whole range of frequencies. The problem is that none of those properties can be achieved in reality. For instance, a filter that has sharp transitions in the frequency domain will have an impulse response h of t with infinite range or width, which implies that the filter would be non-causal. Requiring that an ideal filter has no phase angle implies that h of omega is a real function. But as we know, if a signal is real valued in one domain, it must be symmetric in the other, so that h of t must be symmetric, which also implies again that h of t is non-causal. To understand why the third property of ideal filters can't be satisfied, we need to have a look at the Paley-Wiener criterion. It says that the integral between 0 and infinity of the logarithm of h of omega's magnitude divided by 1 plus omega squared d omega has to be greater than minus infinity for any filter that has a causal impulse response. But if h of omega would be 0 for a range of frequencies, then the logarithm of its magnitude would be minus infinity, which would lead to the integral being equal to minus infinity and not greater than minus infinity. This shows that no causal impulse response h of t can have a frequency response which is 0 for a whole range of omegas. To avoid those issues, which imply that no ideal filters exist, the specifications or characteristics of ideal filters have to be relaxed. Instead of requesting sharp transitions as in ideal filters, realistic filter specifications will allow a transition band. Next, instead of requesting that h of omega is real, which means that it doesn't have a phase angle, the frequency response is allowed to have a phase angle, and the specifications are formulated for the magnitude of h of omega. And instead of requesting that h of omega is equal to 0 for a whole range of frequencies in the stop band, it's only required that the frequency response of the real filter achieves the desired stop-band attenuation for all frequencies within the stop band. Let's have a look at typical specifications for a realistic low-pass filter, which are given for the magnitude of the frequency response. Specifications for the phase of the frequency response are often not considered. First, instead of requiring that the frequency response of the low-pass filter is exactly equal to 1 in the pass band, the frequency response is to vary a little bit, namely in the band between 1 minus delta p and 1 plus delta p. Also, instead of requiring a sharp transition at a cutoff frequency omega c, the realistic filter specification gives a passband frequency omega p and a stopband frequency omega s, such that for all frequencies up until omega p, the frequency response is in between the band 1 minus delta p and 1 plus delta p, and for all frequencies above omega s, the magnitude of the frequency response is required to be below delta S. So instead of only specifying a pass band and a stop band, a transition band is also specified. The cutoff frequency of a realistic filter h of omega is then defined to be the frequency for which the magnitude of the frequency response is equal to 1 over the square root of 2, which is equal to 0.707, which is roughly equal to -3 dB. These kind of filter specifications don't only exist for low-pass filters, but also for high-pass, band-pass, and band-stop or notch filters. Here you see those realistic filter specifications together with one filter which meets the specifications. The low-pass filter shown here is a Chebyshev filter of type 1, the high-pass filter is a Butterworth filter, the band-pass filter is a Chebyshev filter of type 2, and the band-stop filter is an elliptical filter.